Guys, welcome to another session on the topic of functions. We have been looking at this topic for a while now. We started from the theory of functions, where we looked at what we mean by mappings. We looked at the idea of the domain and range of a mapping. We looked at relations and then focused on a special category of relations called functions. And then in the discussion of functions, we looked at composite functions and inverse functions. The next step of the discussion is going to be on types of functions. So we will focus on the specific types of functions, such as linear, quadratic, and other polynomial functions. We'll go into rational functions and so on. But before we do that, we need to go and look at a special area of the discussion on function, and this is about what we call odd and even functions, okay? So even functions, these even and odd functions are a special subset of functions with useful manipulative properties that are applicable both in mathematics and physics. We shall apply some of these properties in our study in this very topic of functions, but we will see how these types of functions are useful when we identify them. We can identify them when we are discussing complex numbers, when we are solving problems involving complex numbers or trigonometry or indeed calculus. We will be able to identify functions that are even or that are odd, and then use these manipulative properties to make our life easier when we are solving real-life problems in these areas, okay? In physics, odd and even functions appear in calculations involving the Schrödinger wave equation and so on, but that is way ahead. You will see how useful this is as you get closer in that section, okay? So let's begin. I'm hoping that we can do this quickly, 20 minutes if possible at the max. Let's see how fast we can go. So we'll start with even functions, and what I want us to do is to approach this from a visual perspective. So what I want is for you to look at these 6 graphs, and I want you to identify any common characteristic of the curves, all right? Think geometrical similarity. So look at the 6 graphs, and do you see any common property that is shared by these 6 graphs, okay? Pause the video and think about that, and if you've done so, we're going to answer the question as we progress, but do look at that, all right? So let's start with even functions. Let's see how we identify even functions, all right? Here is another even function. Let's look at this a little more closely. I'm making use of a quadratic function. This quadratic function is even. Not all quadratic functions are even, but this one is, okay? So looking at this function, let's pick a value of x, an input value of x equal to -2, for example. So when x is -2 there, what is the value of y? So as usual, we read upwards to the curve and then read across to the y-axis, and we can see that when x is 2, the value of y is 3, which is to say that f of 2 is actually 3. But we can see that f of 2 is also 3, which is to say that f of -2 is the same as f of 2, and both of them are equal to 3, okay? This is an important result. We can try other values, okay? We can try other values and see what's going on. What if we took f of -4? So f of -4 is appearing right there, and compare with f of 4, again you can see that f of 4 is 0 and f of -4 is also 0. So f of -4 is the same as f of 4 and is giving us a value there of 0. Okay? Equivalently, we can see that if we took f of -1, you can see there that f of -1 is also the same as f of 1 which you can see is equal to 3.75. And if you look at the blue dotted line, we can also see that f of negative 3 is the same as, so f of negative 3 there is the same as f of 3, and that is giving us a value of approximately 1.75. Of course, we could find this by simply substituting the value into the function. So if you put that there, we would get 9 over 4 there, and 9 over 4 is 2.25, so 4 minus 2.25 would be 1.75, okay? So we could use algebraic approach to find f of negative 3, but I want us to look at this by looking at the graph, okay? Visual representation. So what we notice from this graph then is that in all scenarios, the value, if we put a value of x for an input x and its inverse value negative x, there exists an output y which is the same, which is to say that we are saying that f of x is always equal to f of negative x, provided we are discussing an even function. So given any even function like this, f of negative x will always be equal to f of x. They'll always give the same y value. I guess my question is, why is this so? What geometrical property of this function or this graph makes it possible that f of negative x is equal to f of x? Why is that the same? Why is that the case? Why are these values going to be the same? If I picked another value somewhere here and I looked for the y value, it's going to be the same as the one on this side. So why is this type of graph giving the result f of negative x equal to f of x? And we want to answer that question, okay? And the reason is that for if a function is even, then its graph is always going to be symmetrical about the y-axis, okay? So all graphs of functions that are even are symmetrical, are always going to be symmetrical about the y-axis, okay? Here is what I'm trying to demonstrate. So if it is symmetrical about the y-axis, then what it means is that at any coordinate point, say point D there, all right, point D is the same distance from the y-axis as point D prime. So D and D prime are at the same distance from the origin. So they are equally away. Their distance from the origin is the same. And that goes for point E, point F, and point C as well. Okay? All right? So that is what it means to say that that a function is symmetrical about the y-axis. So if we look at this part of the graph on the negative side of the opposite side of the y-axis, it always maps onto the same points on the right-hand side of the y-axis. So if the x-coordinate on this side, the x-coordinate of point C here is 2, the x-coordinate of point C there is negative 2. Okay? The same, the x-coordinate of point D is 3 there, and the x-coordinate of point D prime is also 3. Okay, so those distances are the same except one is on the opposite of the other. We say that there is symmetry about the y-axis, and all even functions are symmetrical about the y-axis, and because of this, it follows that if you look for the y value of this point, it's going to be the same as the y value of that point. And that's the reason why the result that f of negative x is always the same as f of x, okay? Here are the even functions, and I want you to notice or to note the nature of the function or the nature of the graph. You can see that is a cosine function. It is definitely symmetrical about the y-axis, as you can see. Okay, here is the graph of the inverse square. All right, f of x is 1 over x squared, and again you can see that this is symmetrical about the y-axis. This is the graph of the modulus function of x. This one is symmetrical about the y-axis. Not all modulus functions will be symmetrical about the y-axis, but this one here is, okay? Here is another one. This is the what we call the Gaussian curve, which we will meet again under normal distribution in probability. Again, you can see that this function is symmetrical about the y-axis. So for all these types of function, f of negative x will always be equal to f of x. Okay, that's an important result. So let's write that in a mathematical form. We say that a function f of x is even. Okay, f of x is an even function if for any input x there is an x, an inverse value of x, so that f of x is always equal to f of negative x. Okay, so if for a function you can show that f of minus x is always equal to f of x, then that function is an even function. So we can show that a function is even either algebraically using that result there, or by sketching the function and looking at the graph to see if there is some kind of symmetry about the y-axis. Okay, let's use this result with some examples that you can get in your exam. All right, so here's the first one. Determine whether the following are even functions or not. Determine whether the following are even functions. So are they even function or they are not? So here's the first one. F of x is x power 4. Well, if we're going to test whether this is an even function or not, we need to look for f of negative x. If we look for f of negative x and compare with f of x and find that they are equal, then we know that this f of x is x power 4 is an even function. If they are not equal, then this is not an even function. So let's see that. So like I said, we want to check if f of negative x simplifies to the same value x power 4. If this happens, then they are even functions. If that does not simplify to x power 4, then this is not an even function. Here we go. So what we do is, in place of x, we're going to put negative x. So what is f of negative x? All right, so this equals, in other words, where there is x, we remove it and put negative x. So we have negative x power 4. We have to put it in brackets so that we are sure that the negative belongs to x. And so the whole thing is being put to the power of 4. Okay, or raised to the power of 4. Now we know that any negative number, if a negative number is raised to the power of an even number, the answer is positive, and if it is raised to the power of an odd number, the answer is a negative. All right, so this is a result that we know. For example, negative 2 to the power of 4 would be 16. But negative 2 to the power of 3 would be negative 8, because 3 would be an odd number. Okay? Now, reasoning from that, then that tells me that whatever we get, whatever the value of x is here, our answer is going to be positive. So this is going to be equal to x to the power of 4. In other words, f of negative x equals x power 4, and that means that this and this is equal to f of x there. So since f of negative x is equal to f of x, we can conclude that the function f of x is an even function. Okay, let's move on. Here's a part B of the question. We want to determine whether f of x is, this function here, is even or not. So once again, we need to look for f of negative x and simplify. So what's f of negative x? F of negative x means where there was x, we remove and put negative x. So we are going to replace that x there, not that negative. The x alone there has to be replaced by negative x. So I've written it with a bracket in it. So this minus here is that minus, and now the x is replaced by negative x. Okay? Now, we can see that that bracket inside, that section inside there, that is going to be positive. The negative of a negative number is a positive number, and so all that is replaced by positive x. And so we can express this, the whole thing simplifies to 1 plus x into bracket squared, like that. Alright, so that is f of negative x. Now if we compare f of negative x with f of x there, we can see clearly that they are not the same. So f of x is not equal to f of x, and because of that, this function f of x is 1 minus x into bracket squared is not an even function. I hope this is clear. Let's see the next. Before we go to the next, I took the liberty to sketch the graph of the function just to confirm, and as you can see, this graph is not symmetrical about the y-axis. It's not symmetrical about the line x equal to 0, which is the y-axis. In fact, it is symmetrical about the line x equals 1, and we can tell that from here. We don't need to worry about that if you haven't done this before. And so clearly this is not, it is a quadratic function, but it is not an even function. So not all quadratic functions are even, okay? So because of that lack of symmetry, we can conclude either through the calculations we did, the algebraic process, or by looking at the graph that this function here is not even. Okay, let's look at another one. Here, these are examples for you to try out. Question number 1. Determine whether the following are even functions. So what you want to do is exactly the process we did with the other ones. In each case, find the value of f of negative x. So substitute negative x there and so there, and then simplify and see if you end up with the same thing. If you end up with the same thing, if f of negative x turns out to be the same as f of x, then you have an even function. If that does not happen, then it is not. So pause the video and I want you to try these out. Question D, in the case of question D, what you want to do is to sketch the graph, because we haven't looked at this yet. I want you to sketch the graph of sine of x to the power of 3, and based on what you see from the graph, determine whether this function is even or not, okay? Well, if you've done so, then here are the solutions, or the answers. You would have to do this algebraically yourself, but if you did this correctly, you should determine that the first one there is going to be even. It's an even function. Part B is also an even function. Part C is not an even function. So if you did it correctly, you should know, you should have found that that function C there is not even. As for the third, the fourth one there, I did sketch the graph. If you sketch the graph either on your calculator or using an online graphical package, you should have shown a graph that looks like that. And based on what you see there, this graph is not symmetrical about the y-axis. The left-hand side does not map onto the right-hand side, okay? And therefore, this is not an even function. Okay? Like that. All right, here is another one. Suppose that f of x, suppose that this function here, where a is a constant, okay, find the value of a given that f of x is an even function. So, what is the value of a here that would make this function even? That is the question we are being asked. And once again, we go by the definition of even functions, which is to say, we look for f of minus x. So the first thing I did, of course, was to open this bracket, okay, to simplify f of x, and that is what we get. So try that out and ensure that is what you're getting when you simplify it out, right? So first of all, you factorize, you should end up with 4 terms, and then if you combine the terms containing x, you should end up with that, okay? Now we want to look for f of negative x, so if we substitute for x with negative x there, this is what we get. Now, of course, the fastest way is to substitute here than in the original equation, but I did it anyway just so that you see another way of solving that. So when we simplify that, we get minus 2x plus 3 in one bracket and minus x plus a in the other bracket. And when you open that bracket and combine like terms, you end up with 2x squared minus into brackets 2a plus 3 close bracket x plus 3a. So this here is our value for f of negative x, and that is our value for f of x. Now we are told that this function is even, which is also to suggest that this must be equal to that. If the two functions are equal, then their corresponding terms must also be equal. That is to say, the corresponding terms must be equal. They are even, it's an even function, so this is true. So corresponding terms must be equal. We can equate the corresponding terms or the like terms. So that term there corresponds to that term, and we know that they are equal, right? Those two terms are the same. Similarly, the second term there and the second term here must be the same. So those two terms are also the same. Okay, since the two functions are equal, the corresponding terms or the like terms must be equal. This is obvious. And the last one there is also obvious. But the middle terms don't look alike, but we don't care. We are told that these functions are equal, therefore that term must be equal to that term. We can discard or ignore the first term and the last term because they are obviously the same, and concentrate on the middle term there. If these two functions are the same, f of minus x equals f of x, since these are even function, then we can equate them. All right, that is to say 2a plus 3x must be equal to negative into bracket 2a plus 3x. Okay, so we can get rid of the x, and those two must be the same. All right, there we go. And so get rid of, we can get rid of the x there, and the coefficients must be the same. 2x plus 3 must be equal to negative 2x minus 3, because the negative goes in or when you open that bracket. Collect like terms together, we get 4a equals negative 6, and therefore a must be negative 3 over 2. Okay, so the value of a that when we put here will render this an even function. The value of a has to be negative 3 over 2. And if you try to sketch the graph with negative 3 over 2 here, you will see that it is a quadratic equation which is symmetrical about the y-axis. Okay? Question number 3. If the quadratic function f of x equals that is an even function, prove that b equals 0. Now I didn't solve this one, but I gave a hint, but the hint was almost the whole solution anyway. So I would want you to do it, but here is the hint. Of course, the first thing is if it is even, then we expect that f of negative x must be equal to f of x. All right, so your task is to find f of negative x, and because this is an even function, f of negative x must be equal to f of x. Once you've equated them, then you want to compare the like terms or the corresponding terms. If you compare the corresponding terms, you should be able to arrive at the result. Here is the hint. You must arrive at the result that b on one side must be equal to negative b on the other. Same thing that we found in question number 2. And if b equals negative b, then it follows that 2b equals 0. Move the negative b to the other side, then 2b equals 0, meaning that b equals 0. Divide both sides by 2, we get b equals 0, all right? So, of course, I have cut a bit, you know, the main part I've left out because I want you to do it yourself. So please try that out yourself, and let's see what you end up with, okay? Question number 4 asks us to prove that the sum of two even functions is an even function. And part B, to prove that the product of two even functions is also an even function. So we will do the first one, and you will use the same idea that we use with the part A to solve part B. Okay? So the sum of two even functions. We're going to let that sum be represented by letter S, so S of x. Okay? First of all, let those two even functions be f of x and g of x, and that means that their sum, represented by s of x, s for sum, will be f of x plus g of x. Okay? Now, of course, because they are even functions, it means f of x must be equal to f of negative x. Similarly, this is an even function, so g of x must be equal to g of negative x. Okay? So, Our task then is now to find s of negative x. If we find s of negative x turns out to be equal to s of x, then we know that we have an even function, okay? So let's find s of negative x. We need to find s of negative x, or we need to show that s of negative x is equal to s of x. What's s of negative x? Well, it means where there is, we come to this, where there is x, we replace with the negative x. So we will do the same there and there. And so we have s of negative x equals f of negative x plus g of negative x, like that. All right, and as we've said, these are even functions, so f of x is the same as f of negative x. So f of negative x is the same thing as f of x, since f of x is an even function. The same goes for g of x. So I can remove f of negative x and replace it with f of x because they mean the same thing. Similarly, I can remove g of x there and replace it with g of negative x because they are equal. And as you can see, the expression for s of negative x is the same as the expression for f of x there. Okay, and so s of negative x is equal to s of x, which is to say that the sum of the even functions is also even. This result is true for in all cases. The sum of any two, or the sum of a number of even function is always even. So if you're adding even functions, you will always end up with an even function. And this is a very important result when at a later date, when we look at Taylor-Maclaurin series, we will see the expansion for cosine of x, and we will see that the series expansion of cosine x is a sum of even functions, okay? We'll see that it's the sum of an x squared and an x power 4 and x power 6, okay? So a constant plus an x squared plus an x power 4 plus an x power 6 and so on to infinity, which makes cosine an even function, okay? Right. This brings us to the end of a discussion on even functions. We're going to look at odd functions next. Okay, let's look at the odd functions. Once again, I want you to look at the 6 graphs that I am going to show now, and I want you to identify any common property. Again, think geometrical property. Okay? Looking at these 6 graphs, can you identify any property that is common to the 6 of them? Once again, I want you to think geometrical property. So without wasting any additional time, you should have been able to see that the graphs of odd functions have a rotational symmetry about the origin. A rotational symmetry of 180 about the origin. What do I mean? Means that if you rotated the function through 180 degrees, it would map onto itself. Okay, so here is a demonstration of what I mean by a rotational symmetry. Okay, so point C, once point C moves through 180 degrees, the graph maps onto itself. And this is what is unique about odd functions. So all odd functions will have a rotational symmetry of 180 degrees about the origin. Okay, let's see that. Here is an example. This is the graph of a cubic function. This one has a rotational symmetry of 180 about the origin. Hopefully this can be seen without any further complication. So this is an odd function. If it has a rotational symmetry of 180 about the origin, then it is an odd function. Remember, if it has a line symmetry about the y-axis, then it is an even function. So this one here is an odd function. Very, very quickly we can see, if we pick any point, let's pick a point. So that's the point x equals 1. What is f of 1? F of 1 turns out to be negative 2. Okay, f of 1 is negative 2. Now, what about f of negative 1? Let's do the same thing we were doing with even functions. So f of negative 1, what does f of negative 1 give us? Well, f of negative 1 is going upwards, and that is going to be 2. So f of negative 1 is 2, while f of 1 is negative 2. We can see clearly that f of 1 is not equal to f of negative 1. They're not equal anymore. However, 1 is the negative of the other. So f of 1 and f of negative 1 are the negative of each other. So if I take the negative of f of 1, I get f of negative 1. So the negative of negative 2 is going to be 2. The negative of 2 is going to be negative 2 here. So 1 is the negative of the other in this case. We can look at other examples similarly. Okay, but we can conclude here that f of negative 1 is the negative of f of 1. This is essentially enough. You can try other values and see that you end up with exactly the same thing. Okay. Here are some other odd functions, and I want you to see the rotational symmetry at the origin. Please take a look, and you can see that is a cubic function, has a rotational symmetry of 180 about the origin. Here is the cube root function. It has a rotational symmetry of 180, as you can see. So part of the function is in quadrant 1, the other part is in quadrant 3. If one part is in quadrant 2, the other part will be in quadrant 4, like that. So they tend to be like that. You can see the trigonometric tangent function, tan of x, is also an odd function. You can see the reciprocal function, 1 over x, is an odd function, okay? This is the sine function, the trigonometric sine. You can see that that is also an odd function. There is a rotational symmetry of 180 degrees about the origin, okay? This is a quintic function. If we open that, we'll get x to the power of 5 as the highest order. So it's a polynomial function of order 5, and you can also tell that it is crossing the x-axis at 5 different places, which is to say it has got 5 roots, okay? You can see that where one root there is negative 1, this one is 1. When one root is negative 3, this one is 3, like that. But it's a rotational symmetry of 180 about the origin. You can see the extended part there is on the first quadrant. The extension on the other side is on the third quadrant, right? The elongated maxima on the second quadrant corresponds to the elongated maxima on the fourth quadrant, and so on. So this is definitely an odd function. Okay, let us conclude about odd function. So due to the rotational symmetry of odd function, we can expect that f of negative a will always be the same as the negative of f of a, which is to say that if I pick a point here, let's say there, then f, this is about 2.5, so f of 2.5 would be a negative number there, and f of negative 2.5 is going to be positive. So one is the opposite of the other. So f of negative a is always the negative of f of a. This is true in every case. We can conclude this mathematically and say that a function is said to be odd. Look at this one here. This is a reciprocal function as well. And we can conclude that, look at that. So f of x is going to be positive there, but f of negative x is going to be negative there. So, okay, we notice that one is the negative, the y values are equal in magnitude, but one is negative while the other one is positive, okay? So f of x is an odd function if for any input x, f of negative of x is equal to the negative of f of x. So notice this is different from the case of even function, because in the case of even functions, f of negative x is exactly equal to f of x. So there is no negative here. Okay? So this is how we differentiate odd functions from even functions. Let's look at some questions related to this in terms of odd function. So we're going to use this same idea to look at to show whether a function is even or a function is odd or not. Okay, but before we do that, let's see. Can you show that this is true using other values of x? So you can pause the video and check if you can tell. For example, this is 2 here, so f of 2 is positive 2, but f of negative 2 is negative 2. Okay, so it's always like that. One is the negative of the other. So f of 1 is 4, as you can see. F of 1 here would be 4. And f of negative 1 would be negative 4. So if you check that carefully, you should see that is true. Okay? Similarly, f of negative 1 is the same as the negative of f of 1. Okay? Like that. Similarly, f of 2 is 2, while f of negative 2 is negative 2. So f of 2 is the negative of f of negative 2, or f of negative 2 is the negative of f of 2. So f of negative 2 here, which is this, is the negative of this, so negative 2. Okay? Right? Let's look at examples of this one. Show that the following are odd functions. Here is the first one. We want to show that if f of x is 3x, then this f of x is 3x is an odd function. So we need to find f of negative x and then compare with f of x. In fact, compare with the negative of f of x, okay? So what do we do? So f of negative x means where there is x, remove and replace with negative x. Where there is x, we will take that out and put negative x there, as you can see. But 3 times negative x is just negative of 3x. But 3x is f of x, so we have negative of f of x, because 3x alone is f of x, so this is the negative of f of x, like that. And so we can conclude then that f of negative x is the same as the negative of f of x, and this is the definition of an odd function. So f of x is 3x is an odd function because it obeys that rule for odd functions. I hope you're getting this. It should not be very difficult. Let's see another one. Okay, show that the following are odd functions. So f of x is x minus x cubed. Once again, in place of x, we will put negative x. And so f of negative x must be negative x minus negative x power 3. Okay, if we simplify that, this is just negative x, and this one, a negative number to the power of an odd number, is negative. So we're going to have negative of negative there, and so that is going to be positive x to the power of 3. I hope you get that. And so comparing this result here with that result, before we do that, we can factorize the negative out, and I will have negative of x into x minus x cubed. So you can see that f of x is the negative of this, which is that. So f of x is the negative, right, which is, this is the same as f of negative x there. And so we can see, we can conclude that because f of x is the same as the negative, since f of negative x, so this here is negative x, since f of negative x here, so this here is a negative. So since f of negative x is equal to negative of f of x, we can conclude that f of x is an odd function. I hope this is clear. Let's see if there's another question there. Question 5, this question is for you. Question number 5 here is for you. For what values of the constants p, q, r, s is the cubic function h of x that an odd function? All right, so if this is an odd function, if we're going to answer this question, we have to look for h of negative x. okay, and then compare coefficient by coefficient. All right, I'm not going to do it, but I'm going to give you the hint. So the first thing, of course, is for us to use the definition for odd function, which is to say h of negative x need to be equal to the negative of h of x, okay? So the negative of this. So what is h of negative x? So we need to show that f of negative x is equal to minus f of x. In our case, it is h, so we must say h of negative x equals to the negative of h of x. Can we show that they are equal? So we need to find an expression for f of negative x. In fact, we are told that this is an odd function, so this must be true, and so we need to find the relationship, compare the left-hand side and the right-hand side, compare the like terms, okay? Or the coefficients of the like term. Now, if you do that, equate the coefficients and then compare the simplified forms. If you do that, this is what you need to do. Okay, so pause the video and try to do it and see if you end up with the same, the result that I'm going to give shortly. Okay, assuming you've done it correctly, this should be your answers. Okay, you should be able to show that P and R are real numbers, where P and R are not zeros, okay, while Q and S must be equal to 0. So the value of P must be a real number, the value of R must be a real number. In other words, on the left-hand side of your equation and the right-hand side, you will end up with P on this side and P on that side, so whatever they are must be real numbers, okay? But Q and S must turn out to be 0 if this is to be an odd function. And if this is to be an even function, then it is P and R that have to be zeros, while Q and S will have to be real numbers, okay? Okay. Question number 6 says, to prove that the product of two odd functions is an even function. I believe I've done this one. We want to prove that the product of two odd functions is an even function. All right. The first thing is, let's talk about the two odd functions. So let the two odd functions, well, it's a hint, but I think I've done most of it. Use the same logic as we used in question number 4 and even functions. So if you do that, which is to say, if you use that same logic, you're going to say that we have two odd functions, f of x and g of x, all right? And if the product is, well, we don't know what the product is, let the product be represented by p of x. So p of x must be equal to f of x times g of x, right? Let's see. Use the same logic as used in question 4 and even functions, right? So assuming you've paused the video and you've tried it out, all right, here is the solution. Let the odd function be, the two functions be f of x and g of x. They are both odd, which is to say f of x must be equal to negative of f of minus x. Or if you like, you can say f of negative x must be equal to the negative of f of x. Okay, and g of negative x must be equal to negative of g of x. Okay, so if they are odd functions, then f of negative x must be equal to the negative of f of x, and g of negative x must be the same as the negative of g of x. Keeping that in mind, now we're going to let the product be represented by, say, a letter p. Let the product p of x be equal to f of x times g of x. Okay, so if we do that, now we know our next part is to look for p of minus x, okay, and see if our p of minus x turns out to be the same thing as p of x. So p of minus x then is equal to, in other words, where there is x, we'll remove and put negative x, right? So p of minus x must be equal to f of minus x times g of minus x. But f of x and g of x are odd functions, which is to say that we can, it's like f of the negative can go to the front, right? It's the same as minus of f of x, okay? Because of that, we can replace that by minus f of x, okay? And this can be replaced by negative g of x, okay? Like that. And a negative multiplied by a negative number is a positive number. And so this is just going to be the same thing as g of x times f of x. So p of negative x is turning out to be the same thing as p of x. The expression is the same. And so because, all right, is it? Yes. And so because p of x is the same as p of minus x, we conclude that this must be an even function. This is the definition of even function. So we can conclude that the product of two odd functions is an even function. This is true in every case. Okay? Every time you multiply an even two odd functions, the result is an even function, always. Okay, question number 7. This one is nice and interesting. Suppose that f of x is an even function and g of x is an odd function. Determine whether the composite function f of g of x is even, odd, or neither. Okay, if we look for the composite function f of g of x, is it going to be even, or is it going to be odd, or is it going to be neither of them? Okay? All right, so the approach is the same as what we've done before. We know what the composite function is, so we are going to represent the composite function with the letter C, so C of x for C for composite. So let the composite function C of x be represented by C of x is that. Okay, our job is to look for C of negative x. So C of negative x then, right, C of negative x must be equal to f of g of, because where there is x you remove and put negative x. So remove the x here, put negative x. We do the same here. So C of negative x is given by that. But wait, g of x is an odd function. So if g of x is an odd function, then g of negative x must be the negative of g of x. Okay? Right? Since g of x is an odd function, it follows that g of negative x can be replaced by negative of g of x. So therefore my C of negative x becomes, it becomes f of negative of g of x. Right? So far so good. And now we think of f. Right? F of x is an even function. If it is an even function, then f of a negative something must be equal to f of that something, which is to say f of negative g of x must be the same as f of g of x. Okay, here we go. Since f of x is even, f of a negative something must be the same as f of the something. Okay, so in other words, we can replace negative g of x with g of x. So this becomes f of g of x. Okay, like that. And this is because f of x is an even function. And now we can see that f of x there, the two of them, c of x there, the composite function there, is the same as the composite of negative x, right? And because those two are equal, we can conclude that the composite function of an even function and an odd function is always even. Okay? So the conclusion is that the composite function of an even function and an odd function is always even. Okay? That is, this is what we got earlier. So the composite function is also even. Okay? I want you to use this result or this approach to try question number 8, which is both question and investigative, right? So question 8 is investigative. We are told that why, we know, actually we do know, you can confirm this by just sketching this. We already showed this function here earlier, and we've also shown this function. So the two of them are odd function, and we also showed earlier that the cosine of x and x power negative 2, we didn't do x I think we did x power negative 2. We showed that these two are even functions earlier. Go back and you will see that we showed the 1 over x squared. We showed it earlier, 2 lines that go like that. Okay, so that is an even function. So these two are even functions while those two are odd functions. So you are given those functions there. First, I want you to use a GDC, that is a graphics display calculator, or an online graphics software like Desmos or GeoGebra. Sketch the function. I want you to sketch the function sine of into bracket x squared. All right. So using a GDC or an online graphing package, show that that is an even function. Okay. Once you've done that, then part B says, first of all, use technology, then use an algebraic approach similar to what we did earlier to determine whether the composite function of two even functions. So, do you think the composite function of two even functions is even, odd, or neither? And you think the composite function of two odd functions is even, odd, or neither. So in question 7, we showed that the composite function made up of one even and one odd is always even. What about two even functions? What about two odd functions? First of all, you can try algebraic method first, and then use technology to confirm your answer, or you can do the opposite. But I want you to try that out to see what category these functions belong in. And you can try to create your own functions using this and test them for whether they are even or odd. Okay? I believe this brings us to the end of this discussion of even and odd function. I hope this makes sense. It is especially important for the HL student to be able to handle even and odd function, and also to be able to apply them when we get to other topics, especially when we get into trigonometry. We need to be able to show that the cosine of negative x is the same as the cosine of x, while the sine of negative x is the same as the negative sine of x. And this is useful when we later we will have to derive a formula for the composite, what we refer to as the compound angle formula for trigonometry. So the compound angle formula requires us to be aware of this knowledge, and when we get into calculus, it's also going to be useful to be able to convert a function that looks very scary into a more representative function using these ideas. Okay? Thank you very much. I'll see you in the next video.